Have you ever looked up at the endless night sky and wondered what secrets it hides? Each distant star you see is a beam of ancient light, a message sent across billions of years, the story of creation, transformation, and rebirth. Somewhere in the vast stillness of space, new giants are being born, igniting the darkness with their brilliance. And as others fade, their endings become the beginning of new worlds, of planets, of elements, of life itself. While we stand here, quietly admiring their twinkling glow, entire lifetimes unfold within those distant suns. Stars are the architects of the universe. They forge every element that builds planets, oceans, mountains, and even the atoms within our own bodies. To understand them is to glimpse the very blueprint of existence itself. A star's life is not merely a sequence of stages. It is a grand cosmic adventure, full of drama, beauty, and all the story written in light and time. Each star follows its own path, unique and yet bound by the same universal laws, from the first spark of birth to the final moments of transformation. In this journey, we will explore how stars come into being, their youth, their maturity, and the powerful final acts that leave behind some of the most mysterious objects in the cosmos. We will uncover how stars shape the chemistry of the universe and how their very existence connects to our own. So, make yourself comfortable, brew a cup of tea, dim the lights. Tonight, we travel beyond our world into the quiet depths of space to witness the eternal cycle of creation, light, and renewal. Now close your eyes and imagine you are floating in the vast ocean of the cosmos. All around you, silence. And somewhere, far away, a new star is being born. Nebulae, the cosmic cradles of light far from Earth. In the silent reaches of the cosmos, where there is no sound and almost no light, exist some of the most breathtaking and mysterious places in the universe. Nebulae. These vast clouds of gas and dust are the birthplaces of stars, immense stellar nurseries where gravity and time weave together to create the very engines of galaxies. Within their glowing folds, countless stars and entire solar systems begin their journey. Imagine one of the most famous of them all, the Eagle Nebula. Located around 6,500 light-years from Earth, it is so distant that the light we see from it tonight began its journey when early humans were first learning to use tools. Captured in some of the most iconic telescope images, the Eagle Nebula appears like a pair of colossal wings, a cosmic eagle ready to take flight. It stretches over 30 light-years across, so immense that if we could somehow see it with our own eyes, it would cover a large part of the night sky. At its heart lies a region of intense star formation known as the Pillars of Creation, a towering columns of gas and dust where new suns are being born. Inside these clouds, hydrogen atoms glow with colors ranging from crimson to violet. This luminous display happens because newborn stars emit powerful ultraviolet light, causing the surrounding gas to shimmer like a living flame. Another remarkable stellar nursery is the Orion Nebula, much closer to us, only about 1,500 light-years away, and visible even to the naked eye on a clear winter night. It is one of the brightest and most studied regions in the sky, home to hundreds of young, hot stars that light up the surrounding clouds with their brilliance. Here, the colors are even richer, deep reds, glowing blues, and vibrant greens. These hues come from different chemical elements: oxygen, nitrogen, and hydrogen, each radiating its own shade of light when energized by the heat of the stars. When you look at the Orion Nebula through a telescope, you are seeing not a single object, but a living mosaic of light and energy, a cosmic fresco painted by physics and time. Yet even these wonders pale beside the largest and most luminous nebula in our nearby universe, the Tarantula Nebula. Located in the Large Magellanic Cloud, about 160,000 light-years away. Named for its web-like structure, it resembles a vast celestial spider stretching its luminous arms across space. Within this nebula are thousands of massive, newborn stars. some hundreds of times the mass of our Sun. These stars burn so fiercely that they heat the surrounding gas to millions of degrees, making the nebula glow in intense blues and purples. The color comes from ionized oxygen and other elements. Reacting to the ultraviolet radiation pouring from these young suns, the Tarantula Nebula is not just a spectacle of beauty, it is a cosmic laboratory of creation, where matter, energy, and gravity continuously shape the next generation of stars and planets. Many of these young stars will live fast and die young, exploding as supernovae, colossal bursts of light and force that tear apart their stellar bodies, yet scatter the raw materials for new worlds. Each of these nebulae, the Eagle, the Orion, the Tarantula, is more than just a beautiful cloud drifting through the void. They are living, changing structures, the very wands of the universe where light itself is born. Every glowing atom within them is part of a story that leads, eventually, to us, to the carbon in our cells, the oxygen we breathe, the gold in our hands. They are factories of light and energy, endlessly creating, destroying, and creating again, shaping the destiny of galaxies for billions of years to come. And though they lie at impossible distances, hundreds, thousands, or even hundreds of thousands of light years away, their radiance still reaches us through telescopes. We do not just observe them, we travel back in time, witnessing the ancient, ongoing miracle of creation that built the very universe we call home. Gravitational collapse, the birth of order from chaos. When we gaze at the cosmic nebulae, they appear tranquil and graceful, vast clouds drifting silently through space. But behind this calm exterior lies one of the most powerful and transformative processes in the universe, the birth of stars through gravitational collapse. At first, a nebula is a huge, almost infinite cloud of gas and dust, a silent ocean where hydrogen atoms and tiny particles of dust drift freely, colliding, merging, and dispersing in endless motion. Everything within it seems chaotic, yet it all obeys one invisible, universal force, gravity. Gravity is the quiet architect of the cosmos. It exists everywhere, pulling on every atom, every grain of dust, every planet and star. Even the faintest attraction between two hydrogen atoms matters, and in the vast emptiness of space, where no wind or friction slows them down, gravity becomes the main sculptor of destiny. When, in a small region of a nebula, the gas becomes slightly denser, perhaps due to the shockwave of a nearby supernova or the collision of molecular clouds, gravity begins to strengthen. The particles start to drift closer together, and this movement feeds upon itself. The denser the region becomes, the stronger the pull grows. Slowly, the nebula begins to fold inward upon itself. Imagine tossing a pebble into a still pond. The ripples spread and then return, overlapping and amplifying. In a similar way, ripples of matter in a nebula reinforce each other, creating dense knots of gas. Over millions of years, these knots contract further and further, and what was once an invisible wisp of cloud becomes a glowing cocoon of energy. Inside, the pressure and temperature rise. The atoms crash together faster and harder, transferring energy, heating the core to millions of degrees. The more the gas compresses, the more intense the heat becomes. Eventually, the core reaches such extreme temperatures that a miraculous transformation begins. Hydrogen atoms fuse into helium, releasing an enormous amount of light and heat. This is the birth cry of a star, at the moment when a one-star cloud ignites and shines for the first time. The dense core that forms is called a protostar, a newborn sun still wrapped in its cocoon of gas and dust. It doesn't yet blaze with the brilliance of a mature star, but it is growing, gathering strength, preparing to illuminate the cosmos. As the fusion process stabilizes, the protostar becomes a true star, a source of constant light and warmth. Its radiant energy pushes back the surrounding gas, dispersing the nebula that gave it life. From the remaining debris, new worlds may take shape of planets, asteroids, moons, and comets, each born from the remnants of the same cloud. Gravitational collapse, then, is far more than just the compression of gas. It is the beginning of creation, the transformation of chaos into structure, of darkness into light. Nothing is truly lost, everything is reborn in a new form. In this quiet and seen dance of countless particles colliding and merging, we witness the profound power of gravity, that invisible hand that shapes galaxies, stars, and perhaps even life itself. From emptiness comes fire, from chaos order, and from dust a new sun rises, marking the dawn of another chapter in the eternal story of the universe. The protostar, a sun in its infancy after the great cloud of gas and dust collapses under the pull of gravity, and new light begins to form within its heart, the protostar. It is not yet a true star, but it carries within it all the potential to become one. Hot, dense, and slowly brightening, the protostar is the universe's way of saying that something new has begun, the quiet spark before the flame. At this stage, gravity continues its patient work. The protostar keeps drawing in gas and dust from its surroundings, growing heavier and more compact. The more material it gathers, the greater the pressure becomes at its core. Deep within, atoms are squeezed so tightly that their collisions release tremendous heat, not yet enough for full nuclear fusion, but enough to make the young star glow softly in the infrared spectrum. The light from a protostar is faint, not like the brilliant shine of mature stars, but it is a promise of what's to come. The heat that escapes from its contracting core warms the surrounding gas to thousands of degrees, giving rise to a soft, ghostly luminosity. Inside, temperatures soar to several million degrees, still short of the 10 million required for fusion, but steadily climbing. Around this young sun, a beautiful structure begins to take shape, a protoplanetary disk. It's a swirling ring of gas and cosmic dust, orbiting the glowing core like a vast halo. Over millions of years, within this disk, dust grains will collide and cling together, forming pebbles, then rocks, and eventually the first outlines of planets, moons, and asteroids. Inside the protostar itself, a great circulation begins. Hot gas rises from the core toward the surface, cools, and sinks back down, creating powerful convection currents that mix energy throughout the star. This inner motion is like a slow, cosmic heartbeat, the first rhythm of a living sun. For now, the protostar exists in a delicate balance. Gravity tries to pull everything inward, while the growing heat pushes outward. It shines dimly, trapped between darkness and full radiance, between creation and maturity. And then, one day after millions of years, the temperature in its heart finally climbs high enough. The atoms of hydrogen collide with such force that they fuse into helium, releasing a flood of energy. In that instant, the star is truly born. Its light breaks free from its dusty cradle, radiating across space, marking the start of a new era. What was once a cold cloud has become a sun, a source of warmth, light, and life for billions of years to come. The formation of stars, the awakening of light. At this stage, the era of the protostar's transformation, the young star flickers and shifts, its brightness unsteady. It pulses softly, as if taking its first breaths. The light we see from it is not yet constant, for deep within, it is still growing, still feeding on the gas and dust that surround it. Every spark, every fluctuation in its glow, is part of the struggle to find balance, a balance between gravity pulling inward and energy pushing outward. Gradually, the star's interior grows hotter and denser. The immense pressure at its core begins to overcome the natural repulsion between hydrogen atoms, forcing them together. And then, for the first time, nuclear fusion ignites. Hydrogen transforms into helium, releasing an unimaginable flood of energy. This moment marks the true birth of a star. It is when the inward collapse halts, and the core stabilizes in a delicate cosmic equilibrium. Gravity's endless pull is perfectly matched by the radiation pressing outward. The star has reached what astronomers call the main sequence, its golden age of stability and brilliance. Now, the star will shine for billions of years. A steady beacon of light and warmth across the universe. It is no longer a fragile newborn, but a living, breathing engine burning, glowing, and giving life to everything around it. In the core, the temperature soars to over 15 million degrees Celsius. Under such extreme pressure, hydrogen atoms fuse together, forming helium and releasing colossal amounts of energy. Every second, our sun converts millions of tons of hydrogen into light energy that takes thousands, even millions of years to journey outward before finally escaping into space as sunlight. Inside, this light doesn't travel in a straight line. It bounces endlessly between atoms, absorbed and re-emitted in a chaotic dance of photons, a dance so intricate that the light we feel on Earth today may have begun its journey long before humanity existed. As the energy rises toward the surface, it enters a turbulent layer of boiling plasma, where massive rivers of hot gas rise, cool, and sink again in constant motion, a cosmic ocean of fire. The surface we call the photosphere appears smooth and radiant from afar, but up close it would shimmer with countless bright cells, each the size of a city, each a window into the roaring energy beneath. The temperature here depends on the star's mass, about 5,500 C for a star like our Sun, but reaching 30,000 Celsius or more in massive blue giants that blaze with fierce, white blue light. Our Sun, the nearest star to Earth, is the perfect example of this stage of star in its prime of life, stable and luminous. By studying it, we learn how all stars live, breathe, and eventually fade from their fiery birth to the day they exhaust their fuel and pass their energy back into the cosmos. The formation of a star is not just a process of physics. It is the awakening of light itself. It is the moment when darkness yields to radiance, and the universe, for a brief eternity, shines a little brighter. The inner layers of the sun, the heartbeat of a star. Now that we've seen how stars are born and stabilize, let's dive deeper into the blazing heart of our own sun to understand how it truly works. Though from Earth it looks like a perfect golden disk, the sun is a complex and dynamic world with multiple layers, each performing a vital role in maintaining the cosmic balance of light and life. At its core, temperatures reach an unimaginable 15 million degrees Celsius, and under that intense pressure, hydrogen atoms fuse into helium, releasing the immense energy that powers everything in the solar system. But this energy doesn't instantly reach the surface. It has to travel through the vast inner layers, the radiative zone and the convective zone. In the radiative zone, which makes up about 70% of the sun's radius, energy travels outward as photons, tiny particles of light. But their journey is painfully slow. Each photon, born in the core, is scattered countless times by atoms, changing direction at random. This chaotic dance means that it can take millions of years for a single photon to travel from the core to the outer layers. It's as if light itself becomes lost in a golden labyrinth before it can escape. Once the energy reaches the convective zone, the process changes completely. Here, the gas becomes cooler and thicker, and radiation alone is no longer enough to carry the heat. Instead, vast currents of hot plasma rise upward, while cooler material sinks downward, creating a constant cycle of motion like a pot of boiling water on a cosmic scale. This convection gives the sun its distinctive surface texture. When the energy finally reaches the photosphere, the sun's visible surface, we can see the results as millions of bright, shimmering granules, bubbling cells of hot gas, each roughly the size of a continent. These granules rise, glow brightly, and fade as they cool, forming a dynamic pattern that covers the sun's face like golden skin. The temperature here is about 5,500 degrees Celsius, enough for the sun to radiate visible light, the same light that warms our world and sustains life. Yet, beyond this layer, something extraordinary happens. The temperature, which should continue dropping, instead begins to rise again, reaching millions of degrees in the solar corona. The Sun's outermost atmosphere. Why the corona is hotter than the surface remains one of astronomy's great mysteries. Many scientists believe that magnetic fields born from the motion of charged plasma within the Sun are responsible. These magnetic fields twist and snap, releasing colossal amounts of energy in the form of solar flares and coronal mass ejections. Sunspots are another manifestation of these powerful magnetic forces. They appear as dark patches on the Sun's surface where the magnetic field suppresses convection, cooling those regions by a few thousand degrees. Though darker than their surroundings, each sunspot is still brighter than the full moon. When magnetic fields shift violently, they unleash solar flares, explosive bursts of radiation that can disrupt satellites, communication systems, and even power grids on Earth. The most massive of these eruptions, coronal mass ejections, send billions of tons of charged particles hurtling through space at nearly the speed of light. When these particles strike Earth's atmosphere, they create breathtaking auroras, the northern and southern lights, dancing across the sky. The Sun's luminosity, the total energy it radiates every second, is staggering, about 3.8 times 10 watts. Enough to power all of humanity for billions of years. It has been shining steadily for 4.6 billion years, and will continue for roughly 5 billion more, before exhausting its hydrogen and expanding into a red giant. When that happens, its radius will swell, engulfing Mercury and Venus and perhaps even Earth. But for now, the Sun is in its golden age, perfectly balanced between gravity and fusion, light and darkness. It is both a destroyer and a creator, a furnace of atoms and a cradle of life. By studying the Sun, the nearest star in our cosmic neighborhood, we glimpse the universal laws that govern all stars, their birth, their radiant lives, and their inevitable decline. Every sunrise we see on Earth is a small reminder of this magnificent truth. The light that touches our world today began its journey in the Sun's core millions of years ago. Types of stars, giants and supergiants. Having explored the life of our Sun, we can now look outward beyond our solar system to see how it fits into the vast hierarchy of stars that fill our galaxy. The Sun, steady and long-lived, is just one example in an astonishing spectrum of stellar diversity. Stars differ in mass, temperature, color, and brightness, each telling a different story of cosmic evolution. Some live for billions of years in quiet stability, while others blaze briefly, burning their fuel in magnificent bursts before collapsing into silence. Among the most inspiring are the giants and supergiants, colossal stars that dwarf our Sun in both size and power. These titans of the cosmos can be tens, hundreds, or even thousands of times larger than the Sun, shining with an intensity so great that their light can outshine entire clusters of smaller stars. Take Aldebaran, for example, the red giant in the constellation Taurus. If it were placed where our Sun is now, its vast, glowing surface would stretch beyond the orbit of Earth. Its luminosity is thousands of times greater than that of the Sun, yet its surface temperature is much cooler, around 4,000 degrees Celsius, giving it a deep, reddish-orange glow. Aldebaran, like all red giants, represents a star in its later years, a star that has exhausted the hydrogen in its core and expanded dramatically as it begins to burn helium instead. But not all giants are red. At the opposite end of the spectrum lie the blue giants and blue supergiants, among the hottest and most powerful stars in existence. Their surfaces can reach blistering temperatures of 20,000 to 30,000 degrees Celsius, and their light radiates in striking shades of blue and white. They are massive, 10 to 50 times the mass of our Sun, and their luminosity can be tens of thousands of times greater. A shining example is Regulus, the brightest star in the constellation Leo. It is several times larger and far hotter than the Sun, a beacon of sapphire light visible across immense distances. Yet, despite their brilliance, blue giants live tragically short lives, only a few million years, because their immense mass causes them to burn through their nuclear fuel at an astonishing rate. Where a star like our Sun will shine for 10 billion years. A blue giant burns itself out in a cosmic instant, leaving behind an extraordinary legacy. When such massive stars exhaust their fuel, they expand even further, becoming red supergiants like Betelgeuse, before ending their lives in spectacular supernova explosions, events so powerful they can briefly outshine entire galaxies. From that cataclysmic death, new wonders are born, neutron stars so dense that a teaspoon of their matter weighs billions of tons, or black holes, where gravity is so intense that not even light can escape. Thus, the giants and supergiants remind us of one of the universe's most profound truths, that creation and destruction are one continuous cycle. From their fiery birth to their explosive demise, these stars forge the heavy elements carbon, oxygen, iron that will one day form new worlds, new suns, and perhaps even life itself. The sun may be modest among the stars, but it too is part of this grand cosmic story, a story written in light, fire, and the endless rhythm of birth and rebirth that shapes the universe we call home. Types of stars: red dwarfs, the quiet majority of the universe among the countless stars that fill our galaxy. One type dominates by sheer number: the red dwarf. Though small, faint, and easily overlooked, these humble stars are the quiet architects of cosmic stability. They make up an astonishing 70% of all stars in the Milky Way, forming the invisible foundation upon which the galaxy quietly glows. Our red dwarf is a small, cool, and dim star, typically between 10 and 50 times less massive than our Sun. Its surface temperature ranges from 2,500 to 4,000 degrees Celsius, giving it a soft, reddish hue instead of the bright yellow-white light we associate with larger stars. Its luminosity can be hundreds or even thousands of times weaker than the Sun's, meaning that even the nearest red dwarfs remain invisible to the naked eye. Yet what these stars lack in brightness, they more than make up for in endurance. While massive stars live fast and die young, red dwarfs burn their hydrogen fuel slowly and efficiently, allowing them to survive for trillions of years, far longer than the current age of the universe itself. In other words, not a single red dwarf that has ever formed has yet reached the end of its life. One of the most famous examples is Proxima Centauri, the closest known star to our solar system, just 4.24 light-years away. Despite its proximity, its faint light is invisible without a telescope. On it orbit planets, one of which, Proxima b, lies in the habitable zone, where temperatures might allow liquid water to exist. The long lives of red dwarfs make them fascinating for scientists studying the potential for life beyond Earth. Their slow-burning cores emit steady light for unimaginable spans of time, creating the ideal conditions for planetary systems to evolve and perhaps even sustain life for epochs far beyond the lifetime of our Sun. In the grand tapestry of the cosmos, stellar mass determines destiny. Massive stars, blue giants and supergiants, live brilliantly but briefly, ending in cataclysmic explosions. Stars like our Sun enjoy a balanced, moderate life of about 10 billion years. Red dwarfs, however, embody cosmic patience, a small, steady, and nearly eternal. They will still be shining when the universe itself grows old and cold. They are the quiet hearts of galaxies, unseen yet ever present, the slow heartbeat of the cosmos. While other stars blaze and vanish, the red dwarfs endure, whispering softly through the ages. Light does not need to be bright to last forever. Nuclear fusion, the fire at the heart of the stars. Now that we've explored the different types of stars and their lifespans, let us travel deeper into the very heart of a star to witness the process that gives it life. This is the source of all starlight, all warmth, and every sunrise that has ever touched our world. It is the great cosmic miracle known as nuclear fusion, the process through which stars are born, live, and eventually die. giving birth to new worlds in the process. At its core, nuclear fusion is the merging of atomic nuclei under immense pressure and heat, releasing colossal amounts of energy. In young stars like our Sun, this takes place primarily through what scientists call the proton-proton chain reaction. Inside the stellar core, where temperatures exceed 15 million degrees Celsius, hydrogen atoms, each a single proton, move so fast and collide with such force that they fuse together. When two protons collide, one transforms into a neutron, forming deuterium, a heavier isotope of hydrogen. This new nucleus then captures another proton, creating helium-3. Finally, two helium-3 nuclei fuse to form helium-4, releasing two protons and an enormous burst of energy in the process. That energy radiates outward in the form of photons, the light that eventually escapes into space and, after millions of years of travel through the solar interior, becomes the sunlight we feel on Earth. But even the mightiest fuel source runs out eventually. Over billions of years, the hydrogen in a star's core is gradually consumed, and as it begins to run low, the core contracts under its own gravity. Temperatures soar higher, reaching 100 million degrees. And a new cycle begins, the carbon-nitrogen-oxygen-CNO cycle. In this more advanced process, carbon, nitrogen, and oxygen act as catalysts that help fuse hydrogen into helium even faster. This reaction dominates in stars more massive than the Sun, where the extreme heat and pressure allow for more energetic fusion. As stars grow older and heavier, they begin to forge even heavier elements. When the core temperature reaches hundreds of millions of degrees, new cycles of fusion ignite, producing carbon, neon, magnesium, silicon, and sulfur. These massive stars become vast furnaces, creating nearly every element found in the universe. However, when a star begins fusing iron, everything changes. Iron and nickel are special. Their atomic nuclei are so stable that fusing them doesn't release energy, but instead consumes it. When the core fills with iron, the delicate balance that sustains the star collapses. Gravity suddenly wins. The core implodes, and the outer layers rebound outward in a titanic explosion, the supernova. In that brief, blinding moment, the temperature reaches billions of degrees, and the violence of the explosion forges the universe's rarest and heaviest elements, gold, platinum, uranium, of the materials that will one day form planets, oceans, and living beings. This is the great cycle of cosmic alchemy in the hearts of stars. Hydrogen becomes helium. In the hearts of giants, helium becomes carbon and oxygen. And in their fiery deaths, the heaviest elements are born. Every atom in your body, every breath, every heartbeat, every trace of gold in your veins was once part of a star that lived and died billions of years ago. As astronomer Carl Sagan once said, "We are made of star stuff. The light of the stars is not only what we see in the sky, it is what we are." The death of a star, the final act of light. Now we arrive at the final chapter in a star's long and luminous life, the grand finale that marks the end of its journey. The death of a star, whether gentle or cataclysmic, is one of the most awe-inspiring events in the universe, a reminder that even in endings, there is creation, beauty, and renewal. For stars like our Sun, the ending is quiet, graceful, and deeply poetic. After billions of years of fusing hydrogen into helium, the fuel in the core finally runs out. Without the constant outward pressure of fusion to balance gravity, the core begins to contract, while the outer layers expand outward into space. The star grows enormous, transforming into a red giant. Its surface cools, its color deepens, and its once stable form becomes vast and trembling. In this swollen state, the Sun will one day engulf its inner planets, Mercury and Venus, and possibly brush against Earth's orbit. But even as it destroys, it also creates its outer layers, rich with elements forged over billions of years, are released into space in glowing waves of gas and dust. This shimmering shell becomes what astronomers call a planetary nebula, a radiant bubble of color suspended in the dark, illuminated by the dying core at its center. For a brief cosmic moment, it glows like a flower made of light, spreading the ingredients of new worlds into the galaxy. At the center, what remains of the star collapses into a dense, hot ember known as a white dwarf, a star's eternal ghost. Though only the size of Earth, it retains the mass of an entire sun, glowing faintly with residual heat. Over billions of years, it will slowly cool and fade, becoming a black dwarf, a cold and silent remnant, the final heartbeat of a once living star. But for the massive stars, those many times larger than our sun, death is far more dramatic. When their cores fill with iron and can no longer produce energy through fusion, gravity collapses the core in an instant. The outer layers fall inward, then rebound in a supernova explosion, the burst of light so powerful it can outshine an entire galaxy for a brief moment. In that cosmic blaze, elements heavier than iron or gold, silver, uranium are forged and scattered across the universe. From that destruction, new nebulae form, and from those nebulae, new stars are born. Sometimes, what remains after such an explosion is a neutron star, an object so dense that a teaspoon of its matter would weigh billions of tons. In even more massive cases, the collapse continues until it forms a black hole, a region of space-time where gravity is so strong that not even light can escape. Thus, the death of a star is never truly an end, it is a transformation. Every atom of carbon in your body, every grain of iron in your blood, every glint of gold on Earth was once born in the heart of a dying star. When we look up at the night sky, we are not only seeing stars that shine, we are witnessing the memory of stars that have lived, died, and given birth to everything we are. Even in death, a star continues to create, and through its fading light, the universe remembers. The fate of small stars, a quiet farewell to light. Not every star ends its life in a cataclysmic blaze. The smaller ones of the modest sun scattered throughout the galaxy die differently. Their endings are not marked by destruction, but by a quiet, lingering beauty that transforms their fading light into one of the most breathtaking sights in the cosmos. When a small or medium-sized star, like our sun, exhausts its nuclear fuel, the reactions that have sustained it for billions of years gradually come to an end. Without the outward pressure from fusion to counteract gravity, the core begins to collapse. At the same time, the star's outer layers expand outward into space, glowing ever more faintly as they drift away. This moment marks the beginning of a delicate transformation, the birth of a planetary nebula. Despite the name, planetary nebulae have nothing to do with planets. The term was coined by early astronomers who, through their telescopes, thought these softly glowing orbs resembled distant worlds. In truth, they are the final, luminous breath of a dying star, vast, colorful clouds of gas and dust illuminated by the last light of the shrinking core. These nebulae are among the universe's most stunning creations. Each one is unique, sculpted into intricate forms by stellar winds and radiation. Their colors vary depending on the elements within. Hydrogen glows red, oxygen shines green or turquoise, and nitrogen adds soft shades of violet and pink. Together, they paint the darkness of space with living color, a cosmic signature of the star's final act. At the heart of this glowing shell lies what remains of the star itself, a dense, radiant core known as a white dwarf. It no longer burns through nuclear fusion. Instead, it glows with the residual heat left over from its long life. A white dwarf is incredibly small, roughly the size of Earth, but unimaginably dense, containing nearly the mass of the entire sun compressed into that tiny space. Its temperature can reach tens of thousands of degrees. But over time it slowly cools, its light fading little by little. It doesn't explode, collapse, or vanish suddenly, it simply grows dimmer and colder, radiating away its last warmth into the universe. Eventually, after trillions of years, when its heat is gone, it will become a black dwarf, a silent, invisible relic adrift among the stars. no longer shining, but still existing, the final, eternal memory of a life once filled with light. There is something profoundly poetic in this quiet ending. The white dwarf is a cosmic monument, a glowing testament to what once was the star that lived, burned, and gave its light to the universe. Even as its brightness fades, it remains a symbol of endurance, of peace after fire. So while massive stars die in fury, small stars die in grace. They do not go out with aurora, they whisper their farewells in colors, leaving behind soft echoes of light that will drift through the cosmos for eternity. Planetary Nebulae, the silent art of dying stars. And so, when a star reaches the quiet end of its life, it does not simply vanish into the darkness. Even in its final breath, it leaves behind something astonishing, the luminous trace of its former glory. These are the planetary nebulae, magnificent clouds of color and light, drifting through the void like cosmic paintings drawn by the fading hand of a star. When a star like our sun sheds its outer layers, the surrounding gas and dust continue to glow for thousands of years, illuminated by the burning ember of its remaining core, the white dwarf at its heart. The result is one of the most ethereal and beautiful sights in the universe, a nebula that shimmers in shades of blue, red, green, and violet, depending on the elements it contains. Hydrogen radiates a deep crimson hue. Oxygen glows in turquoise and green. Nitrogen paints the space with soft violets and pinks. Together, these colors weave a story of transformation, of fire turned into beauty, of light returning to the darkness that birthed it. Each planetary nebula has its own unique structure. Some are perfectly spherical, others spiral outward like galaxies in miniature, while some form delicate filaments resembling wings or flowers. This diversity comes from the way the star's winds and magnetic fields interact during its final years, shaping the gas into patterns that can be seen from across the galaxy. At the center of these glowing remnants lies a white dwarf, a tiny but incredibly dense relic, the silent witness of the star's once blazing heart. It no longer fuels nuclear fire, but it continues to radiate faintly, surrounded by the delicate remains of what was once a sun. There is a deep poetry in these endings. A planetary nebula is not merely the death of a star, it is its transformation into art. It is the star's final act of creation, painting its memory across the fabric of space before fading into eternity. Though they fade with time, these celestial sculptures remind us that nothing in the universe truly disappears. Every star leaves a legacy, a whisper of light, a trace of color, a quiet echo that endures for millennia. And even as they fade, the planetary nebulae still glow faintly, like cosmic memorials to the brilliance that once was the soft, eternal farewell to the universe. Neutron stars and black holes. When light collapses into darkness, the supernova, the explosive death of a massive star, marks one of the most powerful moments in the universe. But what happens after the blinding light fades depends entirely on one thing: the star's mass. It is this single factor that determines whether the star's remains will become a neutron star, one of the densest objects known to science, or collapse even further into the mysterious abyss of a black hole. It begins long before the explosion, in the heart of a star much larger than our sun, at least 8 times its mass. Throughout its lifetime, this giant fused hydrogen into helium, helium into carbon, and then, in its final moments, built heavier and heavier elements: oxygen, silicon, and finally iron. Iron marks the end of a star's ability to sustain itself. And like lighter elements, the fusion of iron does not release energy, it consumes it. The balance between gravity pulling inward and radiation pushing outward collapses in an instant. The core begins to fall in on itself, a process so violent that in just a fraction of a second, the star's center reaches tens of billions of degrees. If the collapsing core's mass is less than about 1.4 times the mass of our sun, the Chandrasekhar limit, the collapse halts, and the star becomes a white dwarf. But when the mass exceeds that threshold, gravity overwhelms everything. The electrons and protons are crushed together, forming neutrons, and the star is reborn as something entirely new, a neutron star. A neutron star is a paradox of the cosmos. Tiny yet infinitely massive. It measures only about 20 kilometers across, but a single teaspoon of its matter would weigh around 10 billion tons, as much as a mountain range on Earth. Inside, atomic structure ceases to exist. Neutrons are packed so tightly together that they behave like a single, continuous substance, a fluid of pure nuclear matter. The forces that hold a neutron star together are extraordinary. It is supported by neutron degeneracy pressure, a quantum mechanical effect that resists further collapse. Its magnetic field can be 1 trillion times stronger than Earth's, and its surface gravity is so immense that if you dropped an object from a height of 1 meter, it would hit the surface at a quarter of the speed of light. Many neutron stars rotate incredibly fast, hundreds of times per second, creating beams of radiation that sweep across the cosmos like cosmic lighthouses. These are known as pulsars. They're rhythmic signals detectable across vast distances. A heartbeat echoing through space. But if the collapsing core is even heavier, more than 2 or 3 solar masses, not even neutrons can withstand the crushing force of gravity. In this case, the collapse continues indefinitely. No known force in physics can resist it. The star shrinks beyond its own event horizon, and a black hole is born. A black hole is the ultimate mystery, of a point where the known laws of physics break down. Its gravity is so powerful that nothing, not even light, can escape. From the outside, it appears as a dark sphere surrounded by an invisible boundary, the event horizon. Anything crossing it is lost forever from the visible universe. Yet, black holes are not merely destroyers, they are engines of creation. Their immense gravitational pull shapes galaxies, powers quasars, and bends spacetime itself. They are the cosmic sculptors of structure, hidden in darkness, yet fundamental to the order of the universe. So, from the collapse of a dying star emerged two of the universe's greatest enigmas, the neutron star, dense and spinning like a cosmic heart, and a black hole, silent and consuming, where even light itself surrenders. In their contrasting natures, one shining faintly, the other forever dark, they reveal the universe's most profound truth. From the ashes of light, new mysteries are born. Neutron stars, the quantum giants of the cosmos. One of the most astonishing wonders of quantum mechanics is that it allows neutron stars to exist at all. These stellar remnants are nature's most extreme laboratories, dense beyond imagination, mysterious, and governed by the strange laws of the subatomic world. A neutron star is born in the violent death of a massive star, in the fiery explosion of a supernova. What remains after the blast is an object so compact that it defies ordinary comprehension. Imagine compressing the mass of the Sun no more than 1 million Earths into a sphere only 20 kilometers wide. That's a neutron star, but density is only part of their strangeness. Neutron stars possess some of the strongest magnetic fields in the entire universe, up to 1 trillion times stronger than Earth's. These magnetic forces twist and stretch space around the star, unleashing powerful bursts of radiation and forming spectacular cosmic phenomena. Some neutron stars rotate at breathtaking speeds, hundreds of times every second. As they spin, beams of electromagnetic energy shoot from their magnetic poles into space. When these beams sweep past Earth, they appear as perfectly timed flashes of light. To us, they seem to pulse rhythmically, hence their name, pulsars. A pulsar is like a cosmic lighthouse, sending its steady signal across the galaxy. Each pulse is a heartbeat of a collapsed star, a relic of something that once burned as bright as the sun. These rhythmic beacons have become some of the most precise cosmic clocks known to science, marking time across billions of light years. In rarer cases, the magnetic field of a neutron star is so incredibly strong that it turns the star into an even stranger object, a magnetar. Magnetars are the most magnetic entities in existence. Their fields are so intense that they can distort atomic structures and tear matter apart. Occasionally, a magnetar releases a burst of energy, a flash so powerful that for a brief moment, it can outshine an entire galaxy. These eruptions are among the most violent explosions the universe has ever known. Yet, there are limits even to the defiance of neutron matter. When a collapsing core is too massive, more than 3 times the mass of our Sun, not even quantum forces can resist gravity's pull. The collapse continues, unstoppable. The star contracts past the point of no return and becomes a black hole. At its center lies a singularity, a point of infinite density and zero volume, where the known laws of physics cease to function. Around it forms the event horizon, a boundary beyond which nothing, not even light, can escape. Neutron stars stand on the edge of existence, between matter and oblivion, between physics and the unknowable. They are both remnants and miracles, proof that even in death, stars can create something more mysterious than life itself. Their pulses remind us that the universe still whispers in the language of light even long after the fire that forged it has gone dark. Black holes. Where time and light disappear, black holes are the most mysterious and uninspiring objects in the universe. Their very name evokes both fear and wonder, symbols of something so powerful that even light cannot escape their grasp. These cosmic abysses are born from the deaths of massive stars and stand among the most extreme manifestations of gravity known to science. Imagine a place where the fabric of reality itself bends inward, where gravity grows so immense that space and time collapse together. When a star with a mass greater than 20 to 30 times that of the Sun exhausts its nuclear fuel, it loses the delicate balance between outward radiation pressure and the inward pull of gravity. Its core collapses in on itself with unimaginable force, compressing all its matter into a single, infinitely dense point of singularity. At that moment, the familiar laws of physics no longer apply. Concepts such as space, time, before and after lose their meaning. Surrounding the singularity lies an invisible boundary known as the event horizon, a one-way threshold from which nothing, not even light, can return. Think of it as a cosmic waterfall. You can drift near the edge, but once you cross the line, the current is unstoppable. Beyond that horizon, all paths lead inward. The size of the event horizon depends on the black hole's mass. For stellar black holes formed from dying stars, it may span only a few kilometers. For the supermassive black holes anchoring galaxies, it can stretch millions or even billions of kilometers. At the center of our own galaxy, the Milky Way, resides such a titan, Sagittarius asterisk, a black hole about 4 million times the mass of the Sun, with an event horizon roughly 17 solar radii across. Yet a black hole is far from an empty void. Around it often swirls an accretion disk, a halo of superheated gas, dust, and stellar debris spiraling ever closer to oblivion. As this material falls inward, it heats up to millions of degrees, glowing in X-rays so intense that astronomers can detect them across the universe. Sometimes, magnetic fields near the poles of a black hole channel part of this matter outward in the form of colossal jets, streams of plasma shooting into space at nearly the speed of light. These jets can span thousands of light years, acting as cosmic beacons marking the presence of a black hole that itself remains invisible. Black holes come in several classes. Stellar black holes, with masses of a few to dozens of suns, formed from supernova remnants. Intermediate black holes, hundreds to thousands of solar masses, rare but crucial in the growth of galaxies. Supermassive black holes, residing at galactic centers, with masses millions or billions of times greater than the Sun's. One of the most famous examples is the black hole in the galaxy M87, whose mass exceeds 6.5 billion suns, the first ever to be photographed. Its shadow captured by the Event Horizon Telescope. And contrary to popular myth, black holes are not cosmic vacuum cleaners. If the Sun were magically replaced by a black hole of equal mass, Earth's orbit would remain exactly the same, though the skies would turn forever dark. Only objects that wander too close are devoured, torn apart by tidal forces in an event known as spaghettification, far from being destructive anomalies. Black holes play a vital role in shaping the cosmos. They regulate galactic evolution, recycle energy and matter, and even generate gravitational waves, ripples in spacetime first detected by scientists in 2015, allowing us to listen to the universe itself. Black holes remind us that even in absolute darkness lies profound order, a frontier where creation and destruction are one and the same. They are not the end of the story but the beginning of a deeper mystery, the point where the universe turns inward to contemplate itself. The end of the stellar journey. Though black holes and dying stars may appear to mark the absolute end, they are, in truth, the beginning of something new. The matter they consume, the elements they scatter, and the energy they release are all woven back into the great cosmic cycle of becoming the raw material for future stars, planets, and perhaps even life itself. Black holes are the alchemists of the cosmos, rewriting the laws of nature and reminding us that even in collapse, there is transformation. Every end becomes a seed of creation. And so, our stellar odyssey draws to a close. We have traveled from the birth of stars within dense, glowing nebulae, the cradles of cosmic light, to their magnificent finals, the quiet fading of white dwarfs, the brilliant explosions of supernovae, and the mysterious silence of black holes. Each star is a universe in miniature, carrying within it the story of creation, destruction, and rebirth. They are not merely distant lights in the night sky, but the architects of existence itself, forging the very elements from which everything is made, including us. Every drop of iron in your blood, every atom of calcium in your bones, every breath of oxygen you take was born long ago in the heart of a dying star. When we look up at the night sky, we are, in a way, looking at our own origin, at the ancient fire that once blazed to make us possible. Stars are not eternal, just as we are not. Yet it is in their impermanence that their true greatness shines. For in their finite lives, they give birth to infinity, to galaxies, to worlds, to the endless rhythm of creation that continues long after their light has faded. This is the legacy of the stars: to burn, to die, and to begin again. They turn their light, their energy, into creation, shaping the universe into what we know and cherish today. Every flicker of starlight is the echo of a cosmic act of birth, the quiet continuation of an eternal cycle that began long before us and will continue long after we are gone. So the next time you gaze up at the night sky, remember, it is not merely a spectacle of distant lights. It is a book written in fire, each page inscribed by a star. Every star holds within it a story of creation, of life, of death, and of transformation. And perhaps, somewhere out there in the vast silence of space, at this very moment, a new star is being born, a newborn sun that will one day illuminate worlds yet to exist, and maybe, just maybe, light the path for those who come after us. This is the endless song of the cosmos, the light that dies only to rise again, reminding us that in every ending, a new dawn is waiting to begin. As we reach the end of our cosmic journey, take a deep breath and let the vastness of the universe settle in your mind. You have traveled among nebulae and newborn stars, witnessed the brilliance of supernovae, and touched the quiet mystery of black holes. Each story, each glowing light in the night sky, is a reminder that creation and destruction are never far apart. They are two sides of the same eternal rhythm. Let this thought accompany you as you drift into rest. You are part of this same grand design. The atoms that form your body were once dust inside ancient stars. Their light flows through you still, quietly pulsing with the heartbeat of the cosmos. So close your eyes. Imagine the soft shimmer of distant constellations fading into the darkness. The universe hums its gentle lullaby, endless, vast, and full of wonder. Sleep peacefully beneath the stars, for in their glow, the story of everything continues, and tonight, you are part of it.